Hey guys, how are you? Let me see. Okay, so now let me open the slides for today's lecture. Somewhere in here, somewhere in here. Okay. We're ready now. Let me see. Okay, so let me share the slides. Hi, Brenda, how are you? Let me see. Here we go. And last time, I seem to remember we made it up to this point in the presentation. And just give me 1 second, just 1 second. Okay, well, we can make some annotations in here. Okay, so we made it up to this point, I think, and hopefully you guys can see the slides. I think you can. So we talked about the far field and the near field, and we mentioned that those two regions exist within the field that is generated by an ultrasound transducer, and we were going to talk about each one of them. And here we go. So the near field, as the name implies, is the one that's closest to the transducer. The far field is the one that's farthest. But beyond that, there are a couple of things that should be marked as noticeable differences between these two regions. The first one is that when you go to the far field, right? I mean, if I were to actually, oops. Okay, I know why. Give me 1 second. Not like this. So, okay. So again, share screen, and here we go. Okay, fine, awesome. If we were to make a cut right through this at a fixed depth, what we would actually see is that in the far field, right? If this is like a distance, like X, whatever it is, and then this would be the pressure, we would have something like this, right? And then it's going down and down and down and down. So we have a beam, right? A main beam that points forward. And we have side lobes that point, somewhere else, but they're really weak anyway, so we don't care about them. If we go to the near field though, right, that's kind of a different scenario, because I can have a cut like this and I can have a cut like this, and you have to forgive my horrible drawing abilities, okay? And in some cases, right, if I am drawing this and this is X again, this is a pressure. In some cases, I'm also going to have something like, some lobe and then some things. But then in some other cases, what I'm going to have is a 0, right? And something like this. So there's a 0 here. And you can see it here. You have, like in this spot, you have something that's very dark, which means that dark bluish, which means that it's close to 0. Here you have something that is more like a high amplitude, like reddish, sort of blackish color, right? So it's alternating in between those. And those are, the two different behaviors. In the near field, right, you're going to see that the extent of the field behaves relatively, or looks relatively constant. Whereas in the far field, like we were discussing in your lecture, you'll see that the beam starts diverging. So in general, in the beam field, things are collimated, but they vary a lot within the field of view, right? In terms of like highs and lows of the pressure. So that's like a very, very bad relationship that you guys had when you were, 15, maybe, and you were breaking up and coming back, every other day. Whereas a far field is like a more stable relationship, right? Where, you know, things are steadily, you still have highs and lows, but everything is, you know, more stable, more predictable, right? And you have a very well defined behavior. So you can see it happens in real life, it happens in engineering too. So in terms of these two regions, right, we can observe them with that graphical example, and we can give explanations as to, you know, why they're different in certain ways. But one of the fundamental questions that arises is how do we, or how can we determine where the far field starts, you know, where the near field ends, which is sort of an equivalent question, right? And there are many ways that you can do that. And one that's very, very useful is you can calculate what's the axial pressure, for example, for a circular piston, right? Which is the example that we're looking at here right now. Remember that we said that, I mean, this would be the circular piston. Axial pressure means along the axis of the transducer, which is in this case, it would be the z-axis, right? That's passing through the center, that's perpendicular, and that's pointing in the direction that the beam of the ultrasound transducer is pointing at. And sort of expected because, again, right, circular symmetry, so on and so forth, right? Okay, so if we calculate it, right, using the equation that we already derived, right, that horrible equation with the integral and stuff, you can actually demonstrate that that horrible expression that's sort of simplified in here, right, results in something that actually doesn't look that horrible, which is this. The magnitude of the pressure is proportional or is equal to, you know, a scale version of a sinusoidal of some semi-horrible argument. Don't get me wrong, again, you can do it for fun, you know, but you don't have to. You can take this expression for granted if you wish, but you can derive it from the one in here. Okay, because if you have learned something, you know, along your education in general studies, you can integrate really well, right? So you can do that integral with no problem whatsoever. Now, this would be an example where you have the pressure along the axis of a circular piston in the specific case where, you know, the radius of the piston divided by the wavelength is equal to 4. And there's a whole bunch of interesting things that you may be able to see, right? One of them is that you have 1, 2, 3, and 4 points where the pressure reaches its maximum value. And for those that are thinking, oh, that's like magic, I mean, it's not really quite so, right? I mean, there's a reason for it. And you should be able to see what the reason for it would be, you know, based on this expression over here. And if not, you know, think about it, and it will very, very quickly make sense to you why that has to be the case. Okay. How many zeros or how many nulls do you observe on the axis of the transducer?
3.
So you're seeing 1 in here, 1 in here, 1 in here. Are those the only ones that you get to see?
I don't know if the first one counts because
no, it doesn't. No, that's a good question. No, it doesn't.
Okay.
Do you see another one?
No, like probably in the asymptote, but
correct.
Long.
So if we go all the way to infinity, right, plus, then you will get to see a final 0, right? So actually in acoustics, right, we are kind of interesting sometimes, and that last 0 is the first 0 for us, right? And this last axial maximum is the first maximum, because these are sort of guaranteed to exist. The minimum at infinity is the 0 that is guaranteed to exist. And then you can start having maximum, minimum, maximum, minimum, maximum, minimum, depending on how many multiples of a wavelength the radius of the circular piston is. Okay. Beyond that, which is, maybe a fun fact for you to, when you go to a club or you have a party sometime, you can just mention this randomly. The reason why this becomes important is, a couple of things. The other line that you get to see, this dashed curve in here, asymptotically would be 1 over, x or z or whatever you want to call it, right? It's like 1 over argument. And you can observe that these two curves are eventually starting to reach one another, right? So you can say from a phenomenological point of view, well, after this, last axial maximum or first maximum, depends on how you want to see it, and this is going to start to slowly, go down. There are no more crazy, maximums and zeros. It's just one maximum, and then it just slowly goes down. So you can think of it as, empirically, a point where you could say, this is where the far field and the near field are separated at. Actually, a lot of people in physics and antenna design would sort of disagree with that, saying, no, I mean, in order for this, or in order for any kind of point to be a meaningful separation in between the near field and the far field, it has to be a point at which these two curves over here have a good match to one another, right? They're really close. They're almost converging to be the same. And that happens, like way, way to the right, as you can observe. But we can study this point in here first, right? Which in this plot happens at radius, or sorry, distance divided by radius equal to 4, right? And you can actually go back to that sort of horrible solution that we had for the pressure along the axis of the transducer. And you will be able to, or should be able to derive that this would have to hold, okay? Z1 would be equal to a to the square divided by lambda minus lambda divided by 4. Many, many times, because we're dealing with transducers that are much larger than a wavelength, right? Then this a squared divided by lambda, is going to be, if it's even equal to 1 wavelength radius, right? Then this would become lambda. Lambda over 4 is, kind of something that you get rid of. Again, in practice, reinforcing this, this would have to be much larger anyway than just, 1 wavelength radius or something like that. So this term kind of goes away and nobody cares about it, right? And we would be left with a squared divided by wavelength, which is, a rule of thumb, cutoff point where you could say, well, after this, sort of starts to look like a far field. Now, again, as you may remember, in this previous slides, it's like, okay, that's this point. And by the way, again, that point was, right? I mean, so it's a point of a square divided by wavelength, right? So if it's the distance divided by a, it would be a divided by the wavelength. And a divided by the wavelength, in this case, it would be 4, right? Because we said that the radius was 4 wavelengths, so that's the reason why, right? Now, again, this point is probably, underestimating things. We're looking at something that's much, much, farther away. Probably something, that's happening like over here or whatnot. So in practice, and there's a reason for this, right? But again, these are the beautiful things that you can say. We're not going to spend a lot of time talking about everything. So in practice, we can actually say that there is a Rayleigh distance, which is actually pi a squared divided by wavelength, right? And pi actually in this case, again, would be like, if you think of a point where meaningfully you would think that these two curves may catch on one another, that would be probably like 10 or something like that, right? I mean, just from looking at this, right? I mean, they're getting really close at whatever this point is, 8 or something. So by 10 or 12, reasonably enough, you would think that they're really, really matching one another. So it's not a factor of 3, because that 3 would make that 4 equals to 12. It's a factor of pi, so it's very close to it. And what is pi times a to the square when you have a circle of radius a?
The area.
The
area.
the area, correct. So it's actually the Rayleigh principle tells you that if you calculate the surface area of a radiator and you divide it by the wavelength, you sort of have an idea of where your far field should be. So it's kind of nice, you know, you can generalize this kind of things, you know, with new knowledge that hopefully makes some sense, and it kind of makes sense. Right? I mean, it's a two-dimensional object, so you would think, you know, the bigger it is in a meaningful term, you know, in terms of, you know, the overall dimensions of it compared to a wavelength is where you would think that, you know, far field and near field somehow, right, should be separated at.
So should we, the second,
yes.
So sorry. So should we ignore the second term to rather use this other expression?
In practice, you know, it's probably, it really depends. I mean, it's because it gets to be complicated, right? When you have more complex radiators. This is just a rule of thumb idea, you know, to tell you how far do you think you should be? And in the end, both terms are interchangeable, you know, like not really from saying, I mean, of course they represent different points, right? As long as you are aware of that. But in terms of having an idea of the order of magnitude of how far away you have to be, I mean, they're really, you know, a close-up scale version of one another. But yeah, probably, I mean, you would be okay to use something like the Rayleigh approximation for the far field and go for a surface divided by wavelength. Thank you.
Okay, thanks.
So that, you know, tells you, like, in general, those equations that we have been looking at, they would be able to show, you know, the oscillations that you observe in the near field. You know, how far away do you have to go until you're not in the near field anymore? And then we get to the far field, and the far field is a very, very interesting creature because of many, many reasons, right? I mean, the first one, again, remember, the property of the far field is just very well behaved. And no joke, again, it's really and literally like a relationship, right? Good and bad relationship. That's where you want to be, right? Stable is good. And you can argue many things, right? I mean, it's diverging, and the beam is not, you know, it's tighter in the near field. And see how this maybe resonates again with the whole relationship thing. You know, it's like, yeah, sure, I know, right? I mean, near field has its good things going on for it, but it's not stable. So you want to go for stable, even if, again, trade-offs in engineering, right? Even if the beam is starting to diverge, you want to go to the far field. And there's a reason farther down the line why we actually want to be in the far field when we talk about focusing within the next probably 5 to 10 minutes, okay? So let's see how we make this work. In the far field, because it's far away, right? And this is where, you know, things starts to get fun. You can make approximations. And there are so many approximations that you can make in physics, right? And the approximations are because we want to integrate, right? We want to calculate this integral over here again, which I'm repeating over and over in different slides, right? And we have to integrate this expression over here, where r is equal to, you know, like something, right? I mean, the square root of sigma squared plus r to the square, where sigma is, right, in itself is x squared s plus y s squared, like the location of the differential element, ds, right, plus r squared, which is like super far away. And the key concept here is that it is super far away, right? And because it is super far away, then hopefully there are some things I can simplify from that expression, right? And one of the things that you can imagine is, imagine that, you know, like sigma is equal to 1 centimeter, right? But r is 1 kilometer. Who freaking cares, right? I mean, very surely that capital R is going to be so close to 1 kilometer, right? The variation introduced by that sigma It's going to be incredibly negligible. So in this term, you know, e to the minus jk capital R divided by capital R, we say that 1 over capital R is approximately equal to 1 over little r. And I hope that we're all in agreement that surely enough, that sort of looks like a good approximation, right? Now, sort of follows along the intuition that, you know, in practice, if R goes towards infinity, then, you know, capital R sort of goes to little r. That kind of makes sense, right? So 1 over capital R sort of can go to, you know, 1 over little r. And that would somehow, right, create the impression that this guy should go to e to the minus jk little r. And as you can see on the right hand side of this, the approximation is actually more involved. You can probably scratch your head and think, where the heck is that coming from, right? Where's the xs and cosine x and ys cosine y? To begin with, can you please let me know what the heck is cosine x and cosine y? And I can tell you, yes, sure I can. Like for example, in here, right, you have three-dimensional vector, right? And this has a unitary vector r hat, right? So if I say cosine theta x, it would be equal to r hat dot product with x hat, a unitary vector in the x direction. Cosine of theta y would be equal to r hat dot product with y hat. And, you know, there should be a cosine of theta z also, right? These are the three, you know, angles that orientate the vector in a three-dimensional space. Okay. Now, and again, sorry for the jumping back and forth. So you can actually demonstrate that this is a valid expansion, and you sort of already know how you can do it, right? But you can also take it for granted and say, okay, you know, it's reasonable. I know Lavarello's not pulling my leg. So it's reasonable to assume that, sure, why not? That's the expansion. But why do you think you need a way more complicated expansion for the exponential term, for the complex exponential term, than the one that we needed for 1 over capital R? I mean, why don't I say these two are equal? It's like, no, they're not. They're actually not approximately equal to. No, the approximation is this. Why do I need a more complex approximation for the exponential term? Complex exponential term, I should say. Does anybody want to guess?
Seems like it can be separated. I remember, I think the next expression resembles a inverse, a Fourier transform.
I mean, that could be a reason out of convenience. But there's another reason, right? Meaning, we're lucky enough that it happens that eventually, because we did this, the equations look nice. But we do this because we cannot make this approximation for the complex exponential. Like this one, we cannot make it. Why we cannot make it? Why not just e to the minus jk little r and we get it over with? What do you think? I don't know how much time, maybe none, and that would be okay, you spend on, you know, looking at things like asymptotic approximations of functions within the context of, you know, function integration. Typically, right, when you want to integrate a function, and this is something that you get to see a lot in electromagnetics, and you get to see a lot in, you know, like physics in general. There are super complex equations that you want to integrate. And you start working on a term that's an idea that's called the dominant term. Whenever you have a function, there is one term that dominates an integral, simply because, you know, it's more complex or it has faster variations, and others that are very, very slowly changing, right? Imagine that you want to integrate, you know, a function that is composed of, you know, like a super slow variation and then, you know, a super fast thing. Like for all practical intents, if I go to this interval over here, that super slow thing is a constant, you know, so I just, you know, take it off the integral because it really, like, it's really not going to change at all, right? But that super fast thing, okay, that kind of has an impact, right? So I focus on analyzing that one. This exponential term is actually cosines and sines in disguise. Okay, and this is very super fast. Let me give you another argument that may be more convincing too. Imagine, right, for the sake of an argument, just for the sake of an argument, that again, you know, like capital R is equal to little r, you know, multiplied by 1.001 or something like that, right? So of course, 1 over r and 1 over little r are going to be the same thing. But imagine that I have, you know, like cosine of k times capital R. That's going to be equal to cosine of k times 1.0001 little r, right? Or something like that. I think I added an extra 0, but you're going to get the point. So that's going to be equal to cosine of k little r, right? Plus 0.001 k times little r, right? I mean, nothing magical in there, right?
Yeah.
But what happens if 0.001 times k times little r is equal to pi? Which can happen, right? Remember, little r is very big, right? So k times little r can be a ginormous number. And, you know, multiplied by 0.001, sure, it may be pi. What happens to it? Then the cosine takes a negative sign. And you can see that in the first example, you know, making this approximation gave me an error in the function that I was evaluating, which was 1 over x or 1 over r, right? Of, you know, 0.001 or 0.1%, right? But in this case, it would give me an error of 200%. It's like the worst possible error that it could get, because cosine can only go between 1 and minus 1, right? This is the worst error that I could get. And you sort of see why we don't make the same approximation, because it may be too gross. And it may generate many, many errors in the way that I'm approximating the function. So I need to have something better. And that something better is that something better is encoding a spatial information and is actually allowing the function, you know, to change, taking into consideration to the contributions of the different elements into making a best or a better approximation for those sinusoidal functions. If we actually do this approximation, like Breno said, yes, it is true, right? We go to the equation down here, right? And the e to the minus j k little r divided by little r can go outside the integral, for sure, right? Why not? And then we are left with the integral of u naught, which is the velocity at which the differential element at location x, s, and y, s is vibrating at, and then some complex exponential in here, e to the j to pi, some f of x times xs plus f of y, ys, dxs, dyx, where fx and fy are just k cosine theta x divided by 2 pi, and same thing with cosine of theta y. Those are just constants, right? So that's okay. And I would ask you, but you have already provided the answer, that is an inverse Fourier transform. Given that u is a real function, right? The inverse Fourier transform and the Fourier transform are sort of the same, up to a complex conjugation, right? So you can safely say that the pressure field is proportional to the Fourier transform of the function u naught, right? If we assume, for example, that every point in the transducer is vibrating at the same speed u naught, like everybody's vibrating at unison, right? Then that function u naught would be a constant multiplying the shape of the transducer. So that Fourier transform, right? Or you can say that the pressure field would be proportional to the Fourier transform of the function given by the shape of the transducer. Which, again, remember, equations are good and dandy, right? And they're very useful and they're very neat. But the importance is how you can generalize that knowledge, right? And just like you learned, well, I have a transducer, and if I want to go to the far field, it's sort of like, you know, I can calculate the surface of a transducer divided by the wavelength. That gives me a rough idea of where the far field kind of starts. You can also say, you know, well, in this case, I know that the far field of the transducer is going to look like, you know, the Fourier transform of whatever shape the transducer has. So if, for example, I have a rectangular transducer, which is probably the shape that you're going to see more commonly, if not almost exclusively, in medical ultrasound, then you know that the far field is going to be, you know, is going to roughly start at, you know, like whatever dimension in X multiplied by whatever dimension in Y divided by the wavelength. And also, you know, that in the far field, the radiation pattern is going to look like what type of function? That will be a question to you.
Like a box function, if it is in a rectangle?
Like a sinc function, right? The radiation pattern is going to look like a sinc function because the sinc function is a Fourier transform of the rectangle function. Correct. Questions up to this point?
Oh, that's why it looked like what you draw in the beginning.
Correct.
Oh.
That's why it looks like what I draw in the beginning. And actually, this is showing you guys how the radiation pattern of a transducer would look like, you know, for, I mean, it has a fixed diameter, right, at 2 different frequencies, right? And you can see that, like in this case, because it's a circle, right? Remember that, like the shape of the transducer is a circle, the Fourier transform would be a Jing function, which is one that is described in your notes for lecture number 3. I think it is the one that coincided with a holiday. And the definition of the Jing function is in here, right? With, you know, the J1 being a Bessel function, right? Of the first order. And it's very similar to the sinc function, right? Just that you replace the sign with a J1. And they sort of look similar too, right? But anyway, so that's how it looks like, right? I mean, that's how the Jing function looks like. And this is how the pressure produced by a circular piston would look like when you're in the far field. Couple of things to mention in here, which are important. Why is the beam for the higher frequency narrower than the one for the lower frequency? That just has to do with the fact that when you actually work your way through the math, right, the pressure field is proportional to a Jing of K times A times sine of theta, where K, you remember, is omega, which is 2 pi F divided by C, right? So you would have the Jing of 2 pi divided by C times F times A times sine of theta, right? So interestingly enough, right, you can see it in 2 different ways. The first one, When you have a fixed radius for the transducer, the higher the frequency, the narrower the main lobe is going to be, because the scaling of the gene function is larger. So it's going to compress more, right? For low frequencies, it expands. For high frequencies, it would compact if you have a fixed radius of the transducer, right? And you can also think about it conversely. If your transducer is operating at a fixed frequency, when is the main lobe going to be narrower? When the transducer is larger or when the transducer is smaller? When is the main lobe going to be broader?
When the transducer is broader, will be
When it's
broader.
larger, right? The larger the transducer, the broader your main width, right?
Yes.
And that is a natural consequence of the scaling property of the Fourier transform, right? Because you know that your radiation pattern would be the Fourier transform of your aperture. If your aperture is larger, right? It's like the scaling function, you make it very large in space domain. The Fourier transform is very narrow in frequency domain. You shorten it in space domain, it gets broader in frequency domain. And it's the same thing that is happening here. And you already know the limiting case, right? What's the smallest that you can make that transducer be? A point source, right? You make it so small that's a point. And what's the Fourier transform of a point? Like the amplitude of the Fourier transform is a constant, right? So for the smallest transducer that you can think, which is a point source, the radiation pattern is the broadest that you can think, and also the most unusable one, right? You cannot use that for anything because it's omnidirectional and, you know, it's like flat. You have no directivity. So in practice, you want your transducer to be as big as possible. And that, you know, could be a very nice point to finish this lecture. Everybody can go home happy, right? Thinking like, well, today I learned something, right? In practice, what we want is transducers to be super big so I can, you know, have a very, very narrow main lobe, right? A very tight ultrasound beam. And here is, you know, where you can actually start looking at these things. And you notice that the horizontal axis here is degree, right? Like angle in degrees, like between minus 90 and 90 degrees. And you get to think, so what would be the actual width of the beam of the transducer in units of distance, right? So, I mean, you can actually say that, right? I mean, this is like something like this, and there is an angle, and this is theta, and I'm at a certain distance, r, and then there is this delta over here, right? So delta should be equal to r times tangent of theta, right? Hopefully I'm right, because I always get confused with this. Which is, you know, like if theta is relatively small, right? It's approximately r times theta, right? It's like r sine theta, because tangent goes to sine, and sine would go to theta, right? So it's r times theta, which again is the simplest calculation of just saying like r times theta, because that's the arc, right? The circular arc that's
Yes.
subtended by those two lines that separate those two radii that are separated by an angle of theta degrees, right? Okay, so it's r times theta, which means that even though, right, even though theta gets smaller, right, there's still the factor of radius or distance in front of it, so I have to be mindful of that. And that, again, seems like an okay thing. Until the moment that you start to realize one tiny thing. Remember that we said that in order for these to hold true, you have to be at the far field. And what did we say about that? What we said was, in order to be at the far field, right, I sort of kind of somehow need to be at a distance that is, you know, surface of the radiator divided by the wavelength. So the bigger the radiator, the farther away you have to be in the far field. And here is where you have that kind of annoying dilemma, right? If I want to have a narrow beam, I need to have a huge transducer. But if I have a huge transducer, in order for me to reach the far field, I have to go farther away than I would if I were to have a small transducer. And very inconveniently, it turns out that if you end up, let's say doubling the size of your transducer, you reduce the beam width by half, but you increase the distance that you have to go to by a factor of 2, which in the end ends up giving you exactly the same beam width that you would have had before, which is very, very inconvenient. Or actually you can, conversely see it in a different way, right? Remember that the distance increases with, right, with a to the square, because the distance increases with a to the square, right? If you double the radius, you have to go 4 times farther. Your beam width will be reduced by a factor of 2, right? So that means that because you're 4 times farther away and you're reducing by a factor of 2, then your beam width effectively increases by a factor of 2. Does that sound logical to you?
I got a little bit lost. Like I understand the formulas, but
You understand why that happens, but you don't necessarily intuitively see why.
yeah, exactly. I can see the derivation from the formulas, but I don't understand why.
Because of this. Think about, it's sort of a process, right? There are so many concepts. Think about what we said last lecture, right? The beam of the transducer is like this, and then we reach the far field and it starts to open up, right? Like a funnel, yeah. Triangle, rectangle, right? Okay. And we said that roughly, what is this thickness equal to?
The width of
the diameter of the transducer, yeah. Right?
Yes.
When I'm in the far field, what's the smallest beam that I can get, roughly? That would be in here, right?
Yeah, like in the beginning.
And in here is roughly the diameter of the transducer anyway.
Yeah.
So you see the point? The point is that if I have a transducer that's 2 times bigger, right? My shortest beam width would be the diameter of the transducer, because there's no other way around it, right? For sure, like if I make it twice as big, what's going to happen is that, well, actually, this is poorly drawn, but this would be, twice as big too. And it would take a long time for this to reach it out. And this would probably diverge, and it would not probably, but it surely will diverge at a lower slope, right? But in the end, you cannot beat physics, right? It's inevitable. You cannot beat physics. That's what it would have to be, because there's no other way around it. Because everything starts, with that moment where we said, is it reasonable for all of you that if I draw a funnel, right, that's what the beam should be. So again, it's math and intuition, right? So every learning process, always think about that, right? So everything that may come as a surprise, right? It may not necessarily be a surprise when you realize that you already thought about it. But this is actually quite annoying, right? Because it's basically telling us, think about it in retrospective. If we didn't have the limitation of having to be in the far field, such that the expressions in the far field were valid, right? So I can be in the near field, and somehow the far field expressions are valid. Then my life would be wonderful, right? Because if that were to be possible, then I would know with certainty that if I make my transducer bigger, right, for a fixed distance, my beam, my ultrasonic beam, would be narrower. The only reason why that doesn't happen with the description we're having right now is because that expression requires me to go very far away when the transducer gets bigger, right? Mm-hmm. And even though the beam itself in degrees gets smaller, in actual distance, it actually gets even bigger, right?
Right.
So there is a way to actually circumvent that. And that way is one of the most fundamental, probably is one of the most fundamental principles in the development of antennas and transducers, which is the principle of focusing, which is actually one of the most important components of the operation of beamforming, which is the one that we'll finish describing in the next lecture. And in short, what it means is the following. If I actually curve the shape of my transducer such that every point in the surface of the transducer is at the same distance of a point in space that will receive the special name of focus, right? If I curve it in that way, then I will know that the pressure field in this plane, right, that passes through the focus obeys the expressions that would be observed in the far field. Okay, so that is actually a given. If you curve the surface of your transducer such that every point in the surface is at the same distance to a point that we call the focus, then for the plane that passes through the focus, far field expressions are valid. And you know, there are so many complicated ways of explaining to you why that happens. But this is again one of the most powerful concepts probably to take away from this particular lecture, because it allows me to do something spectacular, which is it allows me to create really tight beams, really tight beams, right? Like these ones. These are transducers are operating, you know, at 9 megahertz or something like that. The beam probably, you know, at -6 dBs or something like that is something like this, which if you read, you know, the scale, the vertical scale, that's probably, you know, 0.1 millimeters, like 100 microns or something like that, which is remarkably small. These are experimentally measured fields. It's remarkably small, you know, compared to anything. I mean, consider that the wavelength, right, for, it says 9 megahertz, should be roughly 1.5 divided by 9, whatever that is, right? I mean, that's something like probably like around, you know, it's less than that actually, but around, you know, 200 micrometers or something, right? 0.2 millimeters to 100 micrometers, which is roughly, you know, like coinciding with the things that we're saying right now. This very bright spot is like probably 0.1, 0.2. If we go all the way to here, it's probably something like 0.4, which is actually 2 times the wavelength. So 2 actually, if you were to go really, really high in frequency, you could, and you will actually have beams that are, you know, like 1 or 2 micrometers in size. That is remarkable, you know, any way you see it. And the expressions that show you, you know, how to calculate it. The other thing to observe is that the beam, however, you know, has a start and an ending point. The beam doesn't stay a beam anywhere. And that, you know, intuitively, you can imagine that it makes sense, right? The expressions in the far field are becoming valid because I curved everything so that they converge into one point. That convergence is going to be great at that point, not so good slightly above and, you know, and beyond. And then the farther away you get from that point, the worse the focusing would be, right? So eventually you start to lose focus, you know, closer to the transducer and also farther away from the transducer. So there's only a reasonably small region of space where that focusing is valid. And that makes sense, right? You here can have the demonstration of what is the width of that beam that you can produce when you curve your transducer like that. And the beam has this width over here, which, you know, I mean, let's get rid of the 1.02 because what the heck, right? Let's call it 1. So it's lambda multiplied by f, which is the focal distance, divided by d, which is the diameter of the transducer. And this little guy has a name that's very important in the literature. That's called the focal number. It's the same principle that you get to see in lenses too, in optics, right? The focal number, you know, is a parameter that defines the quality of focusing of your system. If the focal number is very, very small, then your beam is very, very narrow. Conversely, if it's large, then your beam is relatively broad, right? So you want it to be narrow, probably you're thinking, right? So you want the F number to be very small. So the one thing is that even though the thickness of the beam, again, it's roughly, right? Like from here, it's roughly lambda times the F number. The length of the beam becomes lambda 7, actually, lambda times F number to the square. And here is a conundrum. If you reduce the F number such that your beam is narrower, you are reducing the extent of your beam or the length of your beam by the square of the reduction factor. That is, if you have a certain beam and you double the size of your transducer at the same focal distance, so that you reduce the F number in half, your beam will be reduced in half in thickness, but the length of your beam will be reduced by a factor of 4, which can make your beam very narrow, but also very short. And very short is not something that's very useful in clinical practice, because you need to have a large field of view, right? I mean, you need to have a long beam. So there is yet another trade-off. You want your F number to be small, but depending on how you do things, you cannot have it to be super small, because then, you know, only a fraction of your image would be in focus and everything else would be out of focus. A way to compensate for that is that many systems, what they do is you define several foci. So there's a focus 1, there's a focus 2, there's a focus 3, right? And you can, for example, have a system where you collect data. You know, you have a system focused at F1, and then another one at F2, and then another one at F3, right? And you can stitch the images that these 3 transducers would produce, you know, so you have one portion of the image, then another portion of the image, then another portion of the image, and somehow most of the image is on focus, right? So you can create those composites of images, which actually is a way that, you know, every echographic image is composed in practice nowadays.
Sure.
With the twist that you don't use 3 different transducers, and I will stop in here, but what you use is an array. we're going to spend the whole next lecture talking about arrays, right? Because this is the epitome of what beamforming actually means. And arrays are actually transducers that instead of being just one vibrating surface, you have several elements that you individually excite. And this would allow you, to do all sorts of really cool and interesting things that we're going to discuss on the next lecture. Yes, I think we had a question.
Oh, I was going to ask if well, you have already answered. Like,
oh, okay, awesome.
Yeah.
Because because in practice you wouldn't be able to be like one transducer, second transducer, third transducer. That's super impractical, right? So, and we'll get to see how just having one transducer that's of array type would help you accomplish that. Okay.
Yeah.
Any other questions? Awesome. Okay, then we're going to stop at this point because it's already 7:10 and you may have our lectures to attend. Thank you for being here, and we'll see each other again on Thursday. Thank you, guys.
Bye, teacher.
Bye.
Bye.
Bye, guys.